got some things cleaned up, but it didn't upload all the files last week, so I'm trying to catch them all up this week. I'm teaching almost full time, so it's really going to be tough getting these caught up before the end of the day. But I think all this class got in there. Okay, I think it's the physics classes that didn't, and then the Tuesday, Thursday classes that didn't. So hopefully they'll catch up in time. Now, sorry, I can hardly talk. The other thing that I did get finished on Thursday, at least I think it's all done, I did get finally your syllabus. If it wasn't updated, I finished updating it. I think this one was sort of screwed up, and I had a lot to do on it. I got the research paper instructions out there. This is all on Blackboard now, under content. I got my locator card filled out, and I'll get back to that in a second. I loaded some websites and YouTube videos and things like this that either I found or other students had found that said they found useful for the course. I put those out there. I got all the PowerPoint slides, at least for the older edition, out there. I don't have the new ones yet, but I can't tell much difference so far. I know there will be some place we'll run into minor differences, but actually for this class there may not be any. It may be only 125 that we have some very minor differences. I believe that was the case last term, wasn't it? Yeah. Okay. And then I got the link to the YouTube videos that we make here. So that's all out there under content. So you can go and see that. I'm going to mark the roll first. Chris. Okay. I think I tried to eat my salad too fast and something went down the wrong pipe. I don't know why. Khalil. Right. I didn't get the email sent yet, but I hope to. I was within that close of getting it. Every time I tried to, something came up and somebody interrupted me and stuff. I didn't get it sent, so I'm going to try to do that probably tomorrow, after morning or afternoon 1. I've got office hours in. I don't today. Kayla. All right, good deal. Peyton. Got it. Colton. Got it. Perfect attendance so far. Stuart. Okay. And Jasmine. Not yet. And Anthony. Not yet. Top part of the alphabet. Right in there. Bottom part. A little to be desired. Okay. In fact, they're not here yet. Okay. Now, I got everything done, and now it sounds like they probably are going to pay me for one overload this summer, which means I have to adjust my office hours because we're supposed to be here more hours if we do an overload. So I've got to go back in and probably do office hours adjustment on the syllabus and on my locator card. But except for that, everything's up to date. I think I told you before I'd probably be here way past 3:30 on Tuesday, Thursdays. Now it's official. I will be here way past 3:30 on Tuesday, Thursday. It's the only place I have to adjust. Well, one other minor thing, but it's reality. I was just trying to fit it in with what we did. Okay, so that's going to be done. Just when I thought I had it done, then things changed, which is sort of, isn't that Murphy or somebody? Something like that. A variation of it, anyway.
Eisenhower said no plans survive his first contact with the enemy.
Say that one more time.
Well, like what Eisenhower said, no plan survives first contact with the enemy.
Right, exactly. Right. Not that any enemies I'm talking about. Okay, but you got it right. All right. The book loves to do these little things at the beginning, and the newer edition of the book, I think there's a different thing, but I believe all of them, maybe not the current one, talk about some type of imaging, magnetic resonance imaging. That's what this is. That's what this old book has too. And basically, with that, you can do things like representing the veins leading into the heart. I would think that would be more the arteries, but it says veins here. Maybe, but this is math book, so it's not biology book. Okay. MRI scanners use the mathematics of Fourier transforms to construct 2- and 3-dimensional images. Okay. Jasmine, right? Okay, great, thanks. All right. If you can find sources that will support this and can tie some math into magnetic resonance imaging, you certainly could write on that. But Fourier transforms big time. You can write on who in the world Fourier was. Pretty interesting character, by the way. If I'm not mistaken, I believe he either fought or was on the staff of Napoleon, with Napoleon, good friend. And then Fourier transforms, however they use, you can do all sorts of things with that. So that's the only reason I even show the slide is that there are some potential paper topics right there. What that has to do, well, I guess application of the integral. Yeah, it's involved with that. Okay. But in the previous chapter, we used the integral to compute areas under curves. And we did that or you should have done that in math, the Cal 1, 125 or whatever you call it, your school. And also to compute areas under curves and net change. In this chapter, we discuss some of the other quantities represented by integrals, including volumes, average values, work, total mass, population, fluid flow, and the list really goes on and on and on. Okay? Now, sorry about my throat. Like I said, I think I just hitting the wrong curve. I mean the wrong. Okay. Sometimes this is back to area of curves, but now we're looking at areas between curves. Now this is a renewable energy generating capacity forecast through 2030. So this would be the time in which we're currently living. However, a lot of things have happened since then. Okay. The area of the shaded region, which has units of power times time or energy. So this is, they haven't listed it well, okay. If this is indeed power times time, it should be gigawatt hours, not just gigawatts. Because power is gigawatts, okay. I'm sorry. The area of the shaded region is power this way times time this way, and that would be energy. So that would represent energy. But then they're labeling this as if, what? This is a math book, okay. Taken from a government report, so okay. But this was one they used to represent additional energy from renewable generating capacity projected to result from the government stimulus spending of this time. This was when the government was trying to get us out of what they call the Great Recession. It wasn't the Great Depression, but the recession we had around 2008, the stimulus spending that they were doing, and they were pouring a lot of it into renewables. And this was what was projected without the stimulus spending, generally carrying on the pattern we had seen before. With stimulus spending, they were hoping it was going to go up to there. My guess is we're probably somewhere in between, but I don't know that for sure either, where we're progressing. We're right along here, so I don't know how far we get. The renewable generating capacity has been going up pretty much leaps and bounds, at least until last weekend, so we don't know what's going to happen there. But anyway, this is an example that you might want to say, what's the change? How much more energy are we going to get out of renewables? You would do that by integrating between this curve and that curve. This would be just due to the stimulus spending. Okay, be actually better if you actually measured it. Again, then this would be your, well, this is projection anyway. This would be the actual, and then how much we actually got out of it. But there's just an example of how you might want to do the area between two curves as opposed to just the area under a curve. But, of course, how you get this, you do the area under this curve and subtract off the area under that curve, so really it's the same math. You just, how you do the steps, okay? So that's sort of the background. Hey, how do we do this? This looks pretty interesting. Let's see if they actually show this. They do. This is what I was just referring to. If the upper graph was this one, the lower graph is the G, upper graph is the reddish one, the other one was the bluish one. The difference between those would be the area in between the additional energy that came about from renewables as a result of the stimulus spending. But one of the things we're going to hit in this is that this is actually the difference in two integrals. If they've got the same variable of integration, same limits of integration, then you can say that's the integral of the difference between those two functions. Just like you saw for continuity, you saw for the derivatives, you saw for all sorts of things back in Cal 1, you see that same principle here. It's basically a linearity principle. Okay. Now, here's some other examples you could have, and this is what I was doing hand waving about, trying to show you before, and hopefully this will be less arm waving and more actually pretty picture. Okay. If you're interested in the difference between the area in between two different graphs, here's an f of x, here's a g of x, the area between the graphs. Now, for this to make sense, and they're going to get to this later, but let's go on and mention it now. For this to make sense, f of x must always be greater than or equal to g of x. Has to be. If f of x ever dips between and you try to do the same application, you're not going to get the right answer. So you are going to require that f of x always be greater than or equal to. They can touch, but they just can't cross between the two graphs. That's what we're interested in finding. Well, that's simply taking the area under f of x between these two limits. That gives you this curve, subtracting off this area, and that gives you the area of the question. So this is a pictorial illustration of that last thing we just said. The integral of the difference between two functions is the integral of the top function minus the integral of the bottom function. That gives you. So the area between the two graphs is the difference in the two areas. The integral, the difference between the integrals of two functions is the integral of the difference of those two functions if you've got the same limits of integration, which generally that'll pan out that way. Let's see if we can do example 1. I think they've got a figure of it here. Let's see. Find the area of the region between the graphs of these two functions. Here's, let me get my pen set up. Okay, well, they've got it written here. It's just sort of hard to read. So I'll blow it up now. I can't write on it until I condense it again. But let's, for right now, blow this up. Okay? Find the area of the region between the graphs of the functions f of x, the upper graph, x squared minus 4x plus 10 minus g of x. No, okay. Where g of x is 4x minus x squared, and we're going between 1 and 3. X between 1 and 3. Now, if you got your text and are looking at it, they put 1 is less than or equal to x is less than or equal to 3. This would work if one or both of those didn't have the equal sign on it. It's still going to be the same because the integral of this line here is immeasurable. Okay, so this could be a dotted line here, a dotted line there, or both, but they did it including 1 and 3. Again, you won't make any difference in the actual calculation. Okay, now, they drew the graph for you. Stand by to see homework exercises and later maybe even test questions. It just says find the area between the two graphs, but it doesn't tell you which is the upper and which is the lower. In those circumstances, it's usually a good idea to sketch the graphs. Okay? Otherwise, you're going to come out with a negative answer and you'll say, this can't be, the area can't be negative. Well, if you put the wrong one on top and the wrong one on the bottom, yes, it could. So numerically, you should get the same. But the other thing that drawing the graph, that would guarantee for you this one didn't dip below that one or this one didn't rise above that one. Because then you would get totally wrong answer because it doesn't fit the criteria. Though they haven't mentioned that yet. So anyway, let's do the math here. How would you do that calculation? I'll have to bring it back down to reality here. What would be the area of the region between those two graphs as indicated there? You tell me what to write. Integral from 1 to 3, excellent. Of what? I heard someone say something, I couldn't make it out. Second?
Minus 4x.
X squared minus 4x plus 10 minus 4x minus x squared dx. Okay. Now, they will be showing you this, but here's how I think of this, okay? Pick a little interval here. We'll be doing this later, but why they didn't show you now and then they later going to show you. What this is, that represents the difference between that is a dx, okay? Very small increment. You could call it a delta x and then take the limit as it becomes a dx. So why not just label it as a dx? That's the width of that little rectangle there, right? The difference in height is this value up here minus this value here. Well, that's this minus that, which is exactly what we've written there. And you're summing all those rectangles from 1 to 3. And that's what your integral is doing. So think of it that way, pictorial. It sort of will sometimes get you out of trouble. What's the first thing you got to do here? Say that again.
We've got to make it so we can integrate that.
Okay. And how would you do that?
Try substituting out similar, but one factor to the other. Can we change that negative to positive?
Very good. What you do is distribute the minus sign inside here. So that, and if you allow me to do it without taking up as much room, drop that. Whoa, didn't mean that. I'm going to lose these two. Those two do you nothing. Okay, and what that made that a minus and this a plus. Because the minus outside the parentheses changed the sign of what was inside. This was a plus 4x minus x squared. Now it becomes minus 4x plus x squared. Okay, so you distribute the minus sign across the parentheses. I just did that. Now what? Combine like terms, and what does that give you? 2x squared minus 8x plus 10. And that's what we're going to integrate, dx. Okay, I think we can do that antiderivative, can't we? What would that give you? Now, wait, time out again. Now when you look at that, you might say, hey, those have a common factor of 2. So if you wanted to take the time to write an extra line, now I don't know if it's worth it to you or not, but I kind of like to keep things as simple as possible. Let's factor out the 2. 2 times the integral from 1 to 3 of x squared minus 4x plus 5 dx. That's a little bit easier, not much, but a little bit. But don't forget the 2. You drug it outside, so don't forget it. And what's the antiderivative of x squared? X cubed over 3 minus 4x x squared over 2, which makes it just 2x squared, right? Last, plus 5x. And what do you do with that? Evaluate it from 1 to 3. Okay? Don't forget your 2. Okay? Now, let's plug in the 3 first, and then we'll subtract off the plugging in 1. Okay, so plugging in a 3 there, what do you get? 9 minus 18 plus, second, 15. Okay, now you're subtracting the 1, so, okay. The signs here love to reach out and bite you where you don't want to be bitten, okay? So be very careful with them, okay? This is a positive 1 here, so it's not going to mess. So basically, just plug in the 1, change all the signs as you're doing. So that, what would this be? Minus 1/3. Second? Plus, but you got a 2 in front of it. Plus 2. Minus 5. Got it? Okay. Oh, that 1/3. Ew, what a pain in the neck. Okay. We didn't say that, did we? All right. Let's combine what we can easily. I like to do these two and make that a plus 10. Going to make it a plus 12. However you want to do it. 2 times, that would be minus 9 plus 10 is a plus 1. Plus 2 is 3. Minus 1/3 would be 2 2/3. Or that would be 2 times 8/3. I think that would be something like 16/3. Let's see what they got. Oh, good for them. They got it right. Okay. Now, you do it however you are most comfortable. I mean, if you like to calculate the first one and then subtract off the calculation of the second one, however you do it, you know, however you see it and understand it the best, that's what you would get. Now, next thing I ask is that sort of a reasonable answer? Well, just looking at the graph here, that looks like it's going from 2 to, let's just estimate 2 to 6. That would be 4. 4 times 3 would be 12. This comes up to be 5, isn't it? Yeah. 5 1/3. And since the rectangle here would obviously be bigger than this, so at least that looks like a good ballpark figure. If I'd have gotten something greater than what did I say, 12, I would have felt very suspicious of it, okay, because this is obviously less than the rectangle that you draw there. So that doesn't guarantee you got a right answer, but at least it tells you're kind of in the ballpark. Does that make sense? Okay. Now, here they say, before continuing with more examples, we note that equation 1, which is you flip back a page, flip back a slide, it was this equation right here. This assumes remains valid whenever f of x is greater than or equal to g of x. And I said, I don't know why they're waiting to say it. You really need to say it now. Because if they ever exchange places there, you're going to not get the right answer, okay? Or you aren't guaranteed the right answer anyway, okay? Even when f of x and g of x are not assumed to be positive, okay? Let's see what that represents, okay? Guess what? If you drop this thing down here, the math still works. It's the upper minus the lower. Move it over here, it still works. I mean, as long as that shape is anywhere on here and you're calculating that, yeah. But the f always has to be greater than or equal to the g for this particular rendition to guarantee you the right answers. Okay? Now they get into what I was showing you before. I'm going to skip that slide and come to this. Basically, you're doing, and I think you probably hit this in Cal 1. If you didn't, get used to it. Riemann sum. That's what, and by the way, there's another potential paper topic. Who in the world is Riemann? Okay? Sounds like a good Irish name, probably German name, right? How did he develop this? You know, what was his process? I mean, there's lots of potential paper topics right there. But this is not the same graph. This is showing y positive, f positive, g negative. Still works, just like we were describing before. And basically what you're doing, you're picking rectangles. Now, how do you do this? You first pick a partition. The partition doesn't have to be evenly spaced, like this is very wide there, more narrow there, maybe a little bit wider there, about the same or a little bit wider there, about the same, maybe a little wider there. I mean, it doesn't matter what your partition is. Most of the time, we're going to choose those evenly done so they'll be close to even partitions. Okay? But what you're measuring is you're estimating the rectangle between these 2 points. Now here they use sort of what they call a midpoint, or it's not exactly a midpoint here, obviously, but something middle of the, in between these two, estimate your height there at that point, and then this rectangle represents the area between those two curves. Not very well, okay? This overestimates, this underestimates, this underestimates, this overestimates. But you balance that out, it's not a bad estimation. With that wide of a thing. This one fits much closer. Over and over slightly there, overestimating there. It's going to be a much better fit there. This one looks like these two balance out, maybe you get a little, but you see that's what a Riemann sum does for you. Now, did you have to pick a midpoint? No, you could have picked anywhere. You could have picked left-hand edge, right-hand edge, or somewhere in between, or just random points in between. Like, these look to be fairly close to midpoints here. This one doesn't look to be a midpoint at all. It's just some point in between. It doesn't matter where you go. What you're going to do is take the limit of this as that interval gets smaller. The difference between dx of I and dx of I minus 1 gets smaller, then all these rectangles, however you measure them, are going to get to be a closer representation. And in the limit, the delta x becomes a dx, and you're just taking the difference between the two functions. And that's exactly what we did. This was the inner part of the integral, and this was the delta x. Delta of x minus g of x, which is this minus that. That's the length of that plane. This minus this. That's this point minus that point. That gives you the length of that rectangle, and the delta x later to be a dx. That gives you the width. Sum those up, which is, when it goes to dx, that's an integral between a and b. Okay. That's what you're doing really on every one of these. Okay. So, and this kind of summarizes what we were just saying. The area between two graphs. And here, why didn't they say this to begin with? I don't know. The y on top minus the y on bottom. The difference between that, whether it's positive, one negative, both negative, it's always going to give you the height. This is going to give you the width. Integrate between, and your Riemann sums between, which when you take the limit, this becomes an integral, and that's going to be your f of x minus g of x. As long as this y is always on top and that y is always on bottom, or they coincide. You just don't want them exchanging. All right, I think we're ready for example 2, which will be this slide. Find the area between the graphs of f of x equal x squared minus 5x minus 7, that's this one, okay, and g of x, which is x minus 12, which is this blue line down here, okay? It says over the interval -2 to 5. Houston, we have a problem. And what is that problem? Let's blow it up so we'll see it a little bit better. What's that? Yeah, the thing is, they flip. From -2 to 1, and guess, they drew the graph for us. Again, stand by for homework, stand by for possible test questions. Not going to have the graph drawn for you. You're going to have to work it out yourself. And be careful in drawing them and find out the interval over which this one's on top and that one on the bottom. This one's on top, that one on the bottom. You have to partition this into two integrals. The first one will be f minus g here from -2 to 1. The second one would be g minus f here from 1 to 5. If you don't do that, you're not going to get the area between. What you get then is this area minus this area, and that's not going to be the same thing. So you'll need to draw your graphs. Thank you very much, they drew it for you here, but when you're doing those homework exercises and more than likely test questions, you're going to have to do the graph first to see if indeed these one stays above the other, or if they invert, and if they do, then you have to find out where that is and set up the integral to get the area between the graphs. Okay? So they did the first part of it for us. Where would we go from here? They say step 1, sketch the region. They did it. Thank you very much. Okay? What's next? You tell me what to write. Integral from -2 to 1, x squared minus 5x minus 7 minus x plus 12. Okay, did it, the subtraction in your head there, and that's going to be dx. Okay? Plus, what next? From 1 to 5 of x minus 12 minus x squared plus 5x plus 7. Very good. Integrate that over dx. Okay? Next, oops, -2 to 1. Combine like terms, that would give us x squared minus 6x plus 5 dx plus the integral from 1 to 5 negative x squared plus 6x minus 5. Hey, they look awful close, don't they? All you did was flip signs. That's all you're doing. You're subtracting one, so the one's exactly the opposite of the other, dx. Okay? So, let's just go from here. Antiderivative of the first one. X cubed over 3 minus 3x squared, right? Plus 5x. And you know, guess what? If you are a little rusty on this, just take a derivative of this and see if you can reproduce that. They undo each other. Sure enough, this would be 3 times 1/3, which is 1x squared minus 6x plus 5. Yeah, that works. You evaluate this one from -2 to 1. Yuck. Okay? Plus, and this almost is the same integral. What would it be? Negative x cubed over 3. No, plus 3x squared minus 5x. Evaluated from 1 to 5. Okay? So let's do these separately, and what do you get? 2. Say again?
No, 8 over 3.
No, 1.
Yeah.
Oh, yeah, okay. 1/3 minus 3 plus 5. I like to do the ones that are easy, okay? Now we do the minus. Now here's where be careful for your signs, okay? It's a minus because you're subtracting the lower limit, right? But you get a -2 cubed, which is going to be -8, so that becomes a plus 8/3. Okay, take this as easily, slowly, orderly, whatever it takes for you to see that you're getting the right answer. Okay, I kind of tend to rush things, and sometimes it bites me. Okay, so the next one. Okay, wait. That would change that to a plus. It would, wouldn't it? Because you're subtracting it. But when you do a -2 in here, that's positive. So that would be 4. So that would be a plus 12. Okay, again, those signs can mess you up. Okay? And then plugging in the last part, it would be a minus. 5 times a -2, which would be a plus 10. So sure enough, watch those signs. I hope I didn't screw anything up. We'll see. Okay? How about the next one?
15 plus 5.
Say that again?
Is that -5?
Don't think so. 125 over 3. You're cubing the 5. So that's I put the minus, the plus. That's a -125 over 3. What next? Plus 75. Minus 25. Okay? Now, minus a minus is going to be a plus. And because the bottom is a plus, you're not going to have any sign change. This is going to be 1/3 minus, because you're subtracting, you're doing the lower one, 3 plus 5. Everybody see that? Okay, again, if you're not seeing how I'm doing it, do it a way that you can track it and follow it and say, yes, I know this is right, okay? Don't trust my shortcuts, okay? Now, let's see what we got. I'm going to try to get rid of those 1/3. I don't know if I'll be successful or not. 1/3 minus 125 thirds, that would be 124 thirds. Negative 124 thirds, right? and that's still not going to get rid of a fraction. I tried, but I couldn't do it. So minus 1/24.
What about adding the 8/3?
Oh, why didn't I think of that? Okay, so that would be 9/3. So let's back up and do that. I didn't even recognize that.
Don't forget you also have another 1/3.
Oh, you got another. Oh, okay. All right. Sorry about that. Okay. All right. I wasn't looking clearly. Okay.
So
Let's start with 1/3 plus 8/3. That's 9/3. Minus 1/25 plus 1/3. Okay, let's see what that gives us.
So negative what?
It's still not,
115?
yeah, so it's still not going to get rid of my thirds, but we'll be okay. That would be 10/3, yeah, negative 1/15. And that's not going to reduce. So I took care of that one. Okay, let's do the other numbers. Here we have 22 and 5 is 27 minus 3 is 24 plus 24. We already get taken care of the thirds. And here we have a 50 plus 2 is 52. Now you do it however you want to. I'm really lazy and try to find short ways. I sometimes mess myself up pretty badly.
Where did the 2 come from?
Minus 3 plus 5.
Oh, yeah, sorry.
Like I said, I'm just plumb
okay,
lazy.
that's fine.
Okay.
And that's 76.
Okay, so 76 minus,
115.
okay, let's see what that would be 38 1/3, right? I don't know if this is any easier. When you subtract that, you're going to get 37 2/3, right? Which would be, I bet you they do it as an improper fraction, don't they? Yes, they do. So what would that be? That would be 21 and 2 is 23, 1/13. Yes, that's what they got. Okay. Now, again, I'll admit to you, my math stinks. I mean, I just go all over the board trying to find the easiest way to do it because I don't have but a limited amount of room to do it. But do it however it takes for you to see you're doing the answer right. Don't try all the shortcuts I do.
Let's see. What about that negative 3? Did we ever?
Here?
Yes.
Okay.
I don't think we ever used that.
No, what I did was 22 and 5 is 27 minus 3. You gave it to me, it's 24.
That's right. Okay.
Yeah.
Okay. Just making sure.
Yeah.
Cool.
I knew some weird person gave it. No, I mean, okay. You did that math for me. Okay. Yeah, you have to make sure you got them all. Okay. So, neatness, bookkeeping, how can I talk about neatness? Look at all over the board, but keep up with what you're doing. And we got 113/3, which is what they got. Now, I can't look at this and say, oh yeah, that looks reasonable, because they have such a weird, see, they didn't even label the y-axis at all, you know, they just showed these as the points. If I were drawing the graph, I would have to label that, and then, you know, I might be able to estimate that as a triangle. I wouldn't want to, but I could, you know, and come up with something there. And I don't know what you would estimate that as, but not even half a circle, but you could estimate that. But it still would be a pretty tough thing to do. Just have to trust the math to keep up with it. And it did. All right. Any questions on that?
This may be a stupid question, but when you're taking the interval, why do you change the signs on the second number? You see what I'm saying?
Oh, that was fundamental theorem of calculus, part 1. That when you have the antiderivative of this of a definite integral, okay, then it's This is the antiderivative of this. They used to call that capital alpha of x. This is little alpha of x. Capital alpha of x, evaluated from there, would be alpha b minus alpha b. That's where that comes from. You're subtracting off the one from down here. Yeah, when it's evaluated. Yeah, but that's why that's there. Good question, though, not a dumb one. Okay, let's look at example 3. And again, they're going to do way too much of the work for you, and here it is. I'm going to blow this up to begin with, just to talk about it, if I can. I think I just can, yeah. All right, here we have calculating an area by dividing the region. Find the area of the region bounded by the graphs of y is equal to 8 over x cubed. That's your red curve here. Y is equal to 8x. That's your blue line here. In hockey, you don't go, never mind, okay. And then y is equal to x. Now, this doesn't look like a y is equal to x. You would think that would be a bisecting the thing. Except you look here, here is 2 on the x scale, there's 2 on the y scale. Obviously, they haven't drawn this to scale. They have compressed the y-axis, expanded the x-axis, so they can see it a little better. So there's y is equal to x on this. Here's 1, 1, 1, 1 there, 2, 2 there. So yeah, that is that graph. Now, how are you going to evaluate the area between those 3 curves? Well, there's no one way to do it, okay? There's no one simple step process here. You're going to have to divide. Now, remember this. You're dividing on your independent variable axis, your horizontal axis. So the first thing you do is take this point right here and bring it down here. And they did the drawing for you. You have to figure out what that point of intersection is. It's where this curve is equal to that. So basically what you do is come up and do that, what I just said. And I'm going to lose the space here. You say 8x is equal to 8 over x squared. Right? That's the point they have in common. The y's are the same. What y value is it? Okay? Well, what you could do is divide everything by 8. Right? All right? And then you can multiply both sides by x squared. X cubed is equal to 1. What's the solution? X equal 1. There are 2 other solutions. Those are complex solutions. Not going there. Leave them alone. Just take that one. So sure enough, for x equal 1, that is where that does. It looks like it here, but you can't trust how it looks. You have to verify that it's x equal 1. And you can then plug in either place. Plug in a 1 here, you get y is equal to 8. Plug in a 1 here, you get y is equal to 8. Yeah, they have the same y values there. So you're integrating first from 0, because that's the point of intersection here, where 8x is equal to x, where 7x is equal to 0, it's where x equals 0. It's got to be, okay? So from 0 to 1, you're taking the difference of this and that. I can do that one. 8x minus x is 7x. That's going to be an easy integral to do. So that's the first one. You see what I'm doing there? Okay, so the first integral is going to be from 0 to 1, 7x dx. Okay, that was the easy part. Now the second integral, and by the way, you need to confirm this too. It looks like the x equal 2. We've got to see if it is. That's where 8 over x squared is equal to x. Okay? Again, multiply both sides by x squared. You get 8 is equal to x cubed. And where is that true? X is equal to 2. So sure enough, that was x equal 2. That's where it is. So that's going to go from 1 to 2. From 1 to 2. And then what's on top? 8 over x squared minus, which one's on the bottom? X dx. Okay. Let me get some of the scratch out of the way here. Guess it wouldn't hurt to leave that in there, but main thing I want to get this. Okay. First one's pretty easy. What would that be? 7. A little louder. X squared over 2. Evaluate it from 0 to 1. I'll do the 0, but we'll come back to that in a minute. Okay. Before I even try to integrate this one, I'm going to rewrite it. Integral from 1 to 2. How do you think I want to rewrite that? (8x to the negative 2 minus x dx). Okay? I don't like to try to find antiderivative of 8 over x squared with my variable being in the denominator. I want to write that as a power function and make that power negative 2. Makes life so much easier. Okay? So let's do that part too. What would this be? Antiderivative of this would be? Okay, let's start with 8. X, that's good. To the negative 1 over negative 1. Remember, you're antiderivating, okay, and these are negative numbers, so you have to take it a step at a time. Next part, x squared over 2. Okay, evaluate that from 1 to 2. All right, let's evaluate that first one first. 7 over 2. I said I would do the second part, minus 0. Okay, so I did that. Okay, take that load off your mind there. Okay, plus, what the first part of that one be? You can go back and write it if you want to, and not a bad idea. Minus 8 over x. Okay, minus x squared over 2. Evaluate that from 1 to 2. Okay, so it'd be 7 halves. I put plus, I really don't want it because that's going to start with oh, good. Whew, I thought it erased everything. Okay. Minus 4 is the first part.
Minus
2. Very good. Plus 8. Okay. This time I think our fractions do deal with us. 7 halves plus 1 half is, which is 4. And this is a minus 4, so I can get rid of all those, and that leaves us 6. Okay, can you believe it? And sure enough, that's what they got to. Now, they do them separately. Yeah, you can do them however you like. As long as you see what you're doing, all the steps are right, okay, and are justifiable, and split it up and go from there. So, several ways to get there, but remember when you're integrating a negative exponent, you increase it by 1, which becomes minus 2 plus 1 is a minus 1, and then that's what you divide by. So you almost messed that one up, but then pretty much got it. Okay, any questions on that? And again, don't feel like you have to do it the way I do it. If you see a easier way or a clearer way, that's the main thing. Something that's clearer for you on how to do it, you do it the way you see, as long as you do all correct steps. That's all I require, because we should wind up with the same answer. All right. Now, sort of hate when they do this. What if they're integrating along the y-axis? Okay. Blow this up to begin with. Where am I? There we are. Okay. If this is what we're doing, we have x as a function of y, and the other part of this is the y-axis, which is where x is equal to 0. Okay? So the region between this and there's a parabola, but it's on its side because you have x as a function of y. You cannot write that as y as a function of x. You could write it in two pieces as y as a function of x, but you cannot write that because y isn't a function of x. Fails the vertical line test. But since you do an x as a function of y, that vertical line test becomes a horizontal line test, and it works okay. Okay. But you still have a problem since it's the region between here. You draw this out, and again, their scale, they didn't show you what the y scale was, x scale was in this case. I'll tell you now, when y is equal to 0, x is negative 9. That's a minus 9 right there.
Yeah, okay.
They didn't show you that. That's a minus 9. So, whereas that's 3 here, this is 9 here. So they've really compressed the x scale and expanded the y scale to make it more visible. Let you see it a little bit. Okay, well, what would you do? You just have to think everything horizontally this time. You're doing, since this is a function of y, y-axis is a function of y, y is x equals 0. I mean, x equals 0. That's the y-axis. So, they drew the picture for you. You'll have to draw it yourself. Since it's a function of y, you're taking dy's. Okay? But up here, it's 0 minus this is your length here. Down here is this thing minus 0. That's your length. Okay? Let's start at the bottom. From the bottom at minus 6, from y equal minus 6, you do the function minus 0, which will just be this function. When you get here, it's the opposite of that function, 0 minus this, right minus left, greater minus lesser. So it would be a minus this from minus 3 to 3, and then this minus 0 from 3 to 6. So you do your dx's, I mean dy's in this case. Please don't do dx's in this case, okay. Do dy's in this case, and of course I'm going to have to shrink back. Yuck. Okay. Do a dy's here. Okay. Okay. Your dy, you could call it delta y if you want to be a pragmatist about it here. That's absolutely right. But it's the right minus left, greater minus lesser. And that would just be, I don't think they actually do this one, do they? But we'll do it. Why not? You start and tell me what to write. Start at the bottom and work your way up. Integral from negative 6 to negative 3. Always good. Okay. But I will do this because I am lazy enough to do this one. Okay. Isn't this that symmetric about the x-axis? This is everything is. So let's just do 0 to 6 and double. Because this would be minus here, this would be plus here, double it. So I like to do that. Would you mind? You don't mind being a little lazy? Okay. Have I told you before my theory of being good at math? You almost have to be a little lazy. Do any of you qualify? No. Oh, a couple of you. The rest of you hard workers, you can still do it. Just, it might be a little tougher on you. So let's go back and do this a little smarter. Okay? Now you can only do this when you have symmetry. This looks symmetric, but you look at it and say, yeah, it is. You're going from 0 to 3. Okay? And what are you there? 0 minus this thing. So that's going to be, how about writing as 9 minus y squared? Isn't that just the subtracting the other? Okay. Plus the integral from 3 to 6 of y squared minus 9. Oh, I left off my dy here and my dy here. And you could put them in parentheses if you want to, whatever floats your boat. So let's see what we've got. Let's integrate the first one. Oh, 2 times this. Don't forget that. You're doubling it. Okay. 2 times okay.
Minus, so
9y minus y cubed over 3. Evaluate that from 0 to 3. And then plus y cubed over 3 minus 9y from 3 to 6. Okay? All right. Don't forget to multiply by 2. Okay, let's evaluate that first. 27 9. Okay. I'll do the next part. 0. Okay. Plus. Ugh. Anyone know what 6 cubed is? About 216, isn't it? 216 over 3, which is 72. Minus 54. But then this one doesn't have a 0 there, so you have to actually do it. Minus 9 plus 27. Got it. Okay, let's see if there's anything that can be made easier. Let's just add the positives and subtract the negatives. 2 times 54 plus 27, 72, 54 plus, that would be 126, right? Minus 18 and 54 would be 72, right? Okay, and this would be 2 times, that would be 54, and that would be 108. Let's see if that's anywhere close. Oh, they didn't do it, did they? So it must be right. Okay. That's how you would do that. Okay. Now let's look at the second one here. This is just sort of a generic here. When you have functions of y rather than functions of x, x is a function of y. In other words, your left-hand edge is h of y, your right-hand curve is a g of y. You're subtracting functions of y, so you have to use your dy. And that makes sense. It will be g of y minus h of y. The larger minus the smaller. That gives you your length, the delta y is your width, and you got it. Okay? So that's how you do the region between two curves. Well, the g of y they have is the greater and h of y is the lesser. And they don't cross. They could touch, but they can't cross. If they cross, then you have to do this kind of thing. This one you wouldn't have symmetry on because neither one of those are exactly symmetrical. Good deal. Any questions on that? Okay. The summary slide for that is this one. This is when you have area between two graphs and you have functions of y rather than functions of x. In other words, your increments are going to be dy's. And I'll just tell you, when they got x's there and they want to label the things, they get a to b, and when they have y's, they do c to d. They're almost constant that way, so you get used to it. So this shows the area. Your y's are going from c to d, c on the lower, d on the upper, and then the x to the right minus the x to the left, whereas before they had y up top minus y bottom. So that's what they're doing here, always greater minus lesser. That gives you your way times your radius dy. So doing the way they illustrated the problem, this one was 1 on the right minus 1 on the left. So, hardly breathe here. All right, let's look at example 4. They figured they hadn't introduced enough weird stuff, so let's do some weird stuff. We want weird stuff, don't we? Okay, is this what you have for your example 4? I want to make sure that I don't have a different book. I mean, I know I've got a different edition.
Yes.
Okay.
Well, it's figure 10 for me.
Okay, it's figure 8 here, right? Okay. So here's example 4. Now, there are extra figures there. Did they throw in an extra problem example I didn't do?
Is this considered example? What is this?
Okay, this one's example 4. The previous one was well, the last one we did was the one that had the 3 curves, and that was example 3.
Yeah, everything's on.
Okay, they just threw in a few extra figures. They didn't do any extra examples. Okay. All right, so let's do example 4, and it's based on this figure. They drew it for you. Guess what? Thank them very much, but you're not going to have this always, so get used to thinking of it. Calculate the area enclosed by the graphs of h of y is equal to y squared minus 1. That's the sideways parabola, which is red here, and g of y, which is is y squared minus 1/8 y fourth plus 1. Now, notice that's a quartic equation. Maximum. Look this up for the first part. Later, I'm going to have to shrink it, but at least for now, we can look at it.
I don't know why they didn't just call it x. You see what I'm saying? On the figure, they named it different than in the problem.
Oh, really?
They said, well, h of y equals y squared minus 1.
Okay, and then
Right?
they call it x. Okay. Yeah.
Isn't that weird?
X is, yeah, it is. Yeah, I wish they had done that too for later on. But the point, the blue line has 3 relative extrema, which means it has to be at least a quartic function. This one's a parabola, so it just has 1. So that sort of helps. I mean, looking at this, you might, that. Okay. So that's what you got there. Now, what are we going to do? Since you got everything as function of y, we want to do our increments in y. But our increments are, oh, and by the way, they show you, but I wouldn't trust them. How do you determine your points,
Where they intersect?
yeah, where they intersect. I couldn't think of the word, sorry. The old gray cells, they are dying fast, okay? You set these equal to each other, and this is where I have to go back. Y squared minus 1/8 y fourth plus 1 yeah, that's how they wrote it here, is equal to y squared minus 1. Okay? One real easy thing you can see right off the top, subtract those away. Gone? Okay.
Subtract 1
No,
and add 1/8.
okay, yeah. Move this to that side and that to that side. Is that what you're saying? Okay, so let's make this 1/8 y to the 4th is equal to, I've changed the sign of that, and that will be, okay, no. Okay, I think it's going to be equal to 2, isn't it? Okay.
It's gonna be positive, right? Or, oh, I see what you did.
Yeah, I'll switch sides at the same time. If you
Yeah.
do this here and this here, that would be, this thing is equal to 2, then I switch sides. I'm really being lazy. Write down as little as possible. I don't have so much room. But let's move from there. What do you get? No, I wouldn't. I would multiply by 8, and that would be y4 is equal to 16.
Okay.
Okay? Y is equal to 2. And it's actually plus or minus 2. Okay? And that's what you got. Y is equal to minus 2 down here, y is equal to plus 2 up there. So yeah, we've got our points of intersection.
So since it's symmetrical, can we do?
Yay! He's thinking lazy, isn't he? Okay? Plus or minus 2. Okay? And guess what? The blue's always on the right, and the red's always on the left. So you only have one set of things. And since both of these are symmetric, or at least they sure appear so, then you can go, and you're doing dy, so from 0 to 2. And that should handle it for you. Just double that. Okay? So,
Now let me ask you this.
yes.
Why would we go from, could we go from -1 to 2?
Okay.
Since it's all.
Okay, you're doing dy's, remember?
Okay.
So your limits always have to be from there.
Gotcha.
If you do the full thing, you'd be doing from -2 to 2, but if you want to have it and bubble it, okay, you know, because of symmetry,
I
then
got you.
go 0 to 2.
I got you.
This is a x.
Ah, okay.
Yeah, that is nothing else. So it's 0 to 2. That's where your dy's are going.
I got you.
And you're going to double
You
that.
saw what I was saying though.
Yeah, I thought that's what you were saying. Okay, so this is going to be twice the integral from 0 to 2 of y squared minus 1/8 y4 plus 1 minus y squared plus 1. Okay. dy. You're doing your dy's this way. I like to draw them in just to remind myself. The dy is this way, this minus that is the length that way. Yeah. Okay, and again, the y squareds are gone. And this will be 2 times. Now, and by the way, these two are going to add to 2 plus 2. Okay. What do you get? Y to the 5th over, say it, 40? 40, okay, I thought that's what you said. Okay. Y to the 5th over 40, and that's a minus, so don't forget the minus there. Plus 2, no, 2y. You're integrating the 2.
That's right.
Yeah. Okay? And we're going to evaluate that from 0 to 2. Be 2 times 32, 40, Okay. Oh, yeah, okay. You can do that. Yeah, that would be 4 over 5. Okay.
And then
Plus 4. Okay.
do you want the second part?
Second?
I was asking, do you want to do the second part because it was 0?
I did it, yeah. I'm sorry. I forgot to tell you I was doing it. Okay. All right. Now,
Is that
3 and a fifth, right? Which would be 3 and 1/5 would be 16/5. Okay. 2 times 16/5 would be 32/5. Let's see how they did. Oh, good for them. They got it right. All right. Any questions on that? Yeah. How did we get that? Oh, I thought you told me. Okay. You increase the y by 1. That gives you 5. You already had a 1 over 8 here, and then you have to divide by this 5. So 8 times 5 is 40. Let's just imagine if that was just that. The y 5th over 5, right? And you do 1/8 times that. Minus 1/4. Okay. Good deal. Okay. There is a summary here that goes over the things we were just doing. Oh, do you have example 5? All right. I thought there might be one there. So, yeah, let me first clear the ink. Okay. All right. Here's example 5. Find the area of the region that is bounded by the 3 curves. Now this figure will not apply, obviously. By the 3 curves, y is equal to x squared. Y is equal to x minus 2 squared. And y is equal to 0. Okay, I think I can go from here if you want to look back. Okay, what's the first thing you better do to it? Yeah, you got to graph it. Okay, so let's come over here and graph that baby. Okay, let me tick off a few points. That means make them mad. I think that may be enough. Help me graph that first one. Give me some points. 0, 0. 1, 1. Minus 1, 1. Give me another couple points. 2, 4. And minus 2, 4. Like the way they put them there, then they disappear. Okay? All right, I think we're all right there. We could do 3, 9, minus 3, 9, 5, 6, 7, 8, 9. Okay. Something like that. Here is the parabola that you start with. Not a very pretty one, but okay. Now, what is y is equal to x minus 2 squared? Come on, pre-calculus algebra, what did you learn that was doing? What? Okay, it's a horizontal shift to the right, 2. Okay, so that means your origin will be here, this point will be here, this point will be here. Okay, now, this point will be here, this point will be here. I don't think we really need to go any further because you see this is going to be, this point will be here, so this is going to be like this. And then here's your last one. So this is the little kind of a triangular looking area there. That's all she wrote, folks. Okay? Now, wish I had drawn this bigger in some senses, but how are we going to find the area bounded by those three curves?
Take our half, that little triangle piece, take it from 0 to 1.
Ah, okay. Not a bad way to go.
Could you double that?
And double that, exactly. Okay? So that looks like a smart way to go here. Okay? Now, if these hadn't been symmetric here, and obviously my graph, they don't look very symmetric, but you know they've got to be. But if they weren't symmetric, and you had to go from here to here, then there's a part of it that says do a delta y, because then you've got to do that, but then you have to change this to a function of y and that to a function of y, which isn't that hard to do, but you could. But seeing that this is going to be symmetric, then just since everything's in terms of x's, let's use the dx's and just go 0 to 1 and double. So that's the approach we'll take. So that'll be 2 times what integral? 0 to 1 of x squared minus 0. I can do that, okay? Dx, okay? Wow. Is it that easy? Afraid so. Okay. Don't demand any money back just because it's easy. What would this be? X cubed over 3 evaluated from 0 to 1. Okay? And this would be 2 times 1/3, which would be, I hope that's the answer you got in your book. I don't have it in mine. 2/3. Way to go. All right. Good deal. Nice for them to give you one that's not really all that awful. Did they do it the same way?
Looks like it.
Looks like it. Okay, good. No, that's fine. There were other ways to do it. That's the simplest way. Okay. So they did use symmetry. Okay, good. Glad they did. All right. Any questions on that? The summary's there. Things we've already talked about. Let's look at the preliminary questions. I think what I'll do is erase the ink that I've got here so I can write anything I need on this. Again, that figure is not. Okay. What is the area interpretation of the integral from a to b of f of x minus g of x dx if f of x is always greater than or equal to g of x? What's the area interpretation of that? It's really easy. Don't try to make it hard. Yeah, it's the area between those two curves. F of x, whatever, remember, always greater than or equal to g of x down here, always less than or equal to f of x. Between a and b is the area between those. Just like this one for y, flip that over and you have it. Yeah. That's all they're looking for. I hope, by the way, let me get some. Now that I've got y'all in my grade book, I use the old roll sheets too. This is 6-1. Good height. Area of the region between blah, 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 blah. Oh, and I didn't say when x goes from a to b. Okay. sort of understood that. Number 2. Is that, okay, still equal to the area between the graphs of f and g if f of x is greater than 0 but g of x is less than 0? And we can put equal signs in there if you wanted to. Is that still the area between the curves?
Wouldn't it be no, because you'd have to double it, kind of like we were talking about the symmetry?
But remember, f of x is always up here somewhere, and g of x is always down here. That's what that's saying. Yeah, it still would be. Yeah. Still would be. So that better be just a yes. Ooh, wrong one. So, yes. Okay. Number 3. Suppose that f of x is always greater than or equal to g of x. Okay. Suppose this on 0 to 3. Okay. And that g of x is greater than or equal to f of x on 3 to 5. Express the area between the graphs over 0 to 5 as a sum of integrals. The first one would be 0 to 3, f of x minus g of x dx plus 3 to 5 of g of x minus f of x dx. Yep, that's what you would get. Okay? Can't think of anything else they'd put there. That would be integral 0 to 3. Yep. Okay. They got it wrong in the back. Sorry about that. They put a minus sign in between the two integrals. I was going to say this before, but their answer's wrong. But if you wanted to leave that in the same order as it was here, so you have to just integrate the same thing, then you put the minus sign here. But they put the minus sign here, but they put it in this order, so they got it wrong. But you could flip these and make that a minus, and then you're perfectly fine. You could keep that a plus, flip these, and keep this just like it is, and that would work too. That's a little weird, but you could do that too. There's several ways you could write it, but since the book was writing it this way, I said, I'll keep my mouth shut and not introduce the other. Well, then they went around and tried to introduce the other, but got it wrong. So anyway, what we said is right. Okay. Number 4. Suppose that the graphs of x equal f of y, let's just clear this out of the way. Okay. Suppose that the graph x equal f of y lies to the left of the y-axis okay, is the integral from a to b. This is surprising. Most of the time they put c to d, but they got it this way this time. F of y dy plus or minus. Okay. Remember, f is to the left over here. Okay? And this would be f minus 0. Well, this is always negative with that, so that would then be a minus. Now, that's assuming a is less than b. If b was less than a, then that would be positive. They didn't say that, okay? So we'll assume that A is less than B. This would be negative. Very good. Any questions on that? All right. Homework exercises. Let's do.
I have a couple
Yes.
other questions.
Okay, sure.
Um,
Oh, in your book. Okay.
5 and 6.
5 and 6. Okay. Let's see. Explain what the integral from A to B of, this says the absolute value of f of x minus g of x dx represents. Oh. Okay. What would that represent? Right. And that would be, yeah, the sum of the areas, not counting whether the areas are plus or minus. You're absolutely right. That would be the sum of all the areas between A and B, because whatever that difference is, whichever's on top, you know, it doesn't matter. That's always going to be a positive thing. So, yeah, you got it. Let's see what their back of the book says on that. They have another way of saying it, and I can't think what their. Yeah, that's okay. The area of the region bounded by the graphs of the functions and the vertical lines. Yeah, x equal A and x equal B. So yeah, exactly what you said. And they just phrase it a little differently. And 6 is draw a region that is both vertically simple and horizontally simple. Now there is something they left out. This new thing talks about what it means to be simple or not, as if simple-minded. Okay. Let me make sure I just didn't skip it. Pretty sure I didn't. No, they don't have those definitions here. So let me give them to you. Okay? Oh, it's fine. Okay. We call a region horizontally simple since every horizontal line that intersects the region does so in a single line segment or point that such that the left endpoint is on the curve x equal h of y and the right endpoint is on the curve x equal g of y. Okay. And this is where the extra figures came in. This is horizontally simple. Because every horizontal line you draw, the right-hand endpoint's on the blue and left's on the red. That's horizontally simple. This would not be vertically simple at all. This part right in here would be vertically simple. If you know it, that would be only if you had that. Or this part right up here would be vertically simple if that was all it was. But obviously not. But that whole graph is horizontally simple. Okay. So that's what they're asking you for here. Does draw a region that is both vertically simple and horizontally simple. Okay. Anyone want to suggest something I could draw?
Could you draw like 2 circles, like, or I don't know.
I could, but it would be,
See what
yeah,
I'm saying?
right.
I was trying to think of some
Yeah.
way that they would both.
Okay. This would be, no, that wouldn't, would it?
Yeah. That's tricky.
Let's see one that we've already had. How about this one that we had? Okay. that would be horizontally simple, and it's also vertically simple. Okay. So something like that, that it can't back up on itself or have to introduce another line to cover it. So I think that would be one. The one they showed in the back, which is just one of many you could have done, was this one. Started off almost okay. Let's do a parabola here and a line here. This is vertically simple and it's horizontally simple. Okay. Glad you pointed those out to me. Okay. All right. Like I was going to say, do either exercise 1 or 3, or both if you choose. Do number 5, do number 7. Then do either 9 or 11 or both, either 13 or 15 or both. Do 17. Do 19 or 21 or both. Do 23, do 25, and then, here's where the big choice comes from. Any of the odds, 27 to 43. They have a whole passel and a half of them there. Okay? 45 says you need a computer algebra system to do it. If you can without it, try it. If you can't, don't sweat it. Don't get too bogged down with it. 47 is mostly a writing problem, but expressing it, but you might want to think through that one. 49 or 51 or both. 53 says you need a computer algebra system, so if you can't figure out how to do that one, then don't sweat that without that. 55. Try to do 55. It's back of John's guitar. 57, even though it may just be a think-through problem, it's the Gini index. Now, this is not talking about a dream of Genie or that kind of genie. It's a someone who was named Genie, I'm pretty sure. I don't remember for sure. But since it is kind of a think-through problem, you can use it instead to actually write on, wait a minute, on who was Genie or how did he or she develop this index and how do you use the index, that type of thing. But I hadn't read from what's right above that, the instructions, is called a Lorentz curve, okay? That's where you use these Gini indices. So who was Lorentz, or how did he develop this curve? What fields would use this? Would your field use it? That kind of stuff. I'll let you decide whether you want to go with one of those. And then further insights, I'll let you look at those if you choose. All right, any questions? 6.1. Okay. Ugh. My head's sort of clogging up on me, sorry. I think that's why my voice was leaving me earlier. Let's go to 6.2. And was he the only one with the book? I want to make sure. I think it is the same section. Setting up integrals, volume, density, average values. All right, it finally came up. Goodness, my eyes are... I think this room is drying me out pretty badly. All right. Again, the title of this chapter is Applications of Integrals. We saw areas between two curves, that kind of stuff. Actually, between three curves sometimes, areas. Another, which quantities are represented by integrals? Roughly speaking, integrals represent quantities such as the total amount of something, total amount of area, total amount of volume, total mass, these kinds of things. There is a two-step procedure for computing such quantities. First, approximate the quantity by a sum of n terms. That would be sort of a Riemann sum type thing. And two, pass the limit as n approaches infinity to obtain an integral. We'll use that procedure often in this and later sections. Okay, so we're going to start with volume. I don't know if you think of this as a cylinder. Technically speaking, it is. Most of the time, when I think cylinder, I think a right circular cylinder. A tin can you buy in the grocery store, okay? But any figure, and typically closed, though it doesn't even have to be closed, that's created by following any curve anywhere in the xy plane and letting z be, perpendicular to the xy plane. Doing that creates a cylinder. This is a closed cylinder, but here your base looks like a shoe print or something like that. As long as the height is constantly the same throughout that process, the shape down here is the same as the shape up here as it is all throughout that shape always reproduces itself. That's a cylinder. Okay? Now, this is a right cylinder, meaning that it is a right angle between the xy plane, say, and the z-axis. That's a right cylinder. You could have one that's a leaning cylinder, that's something quite different. Okay? But the volume of any right cylinder is the area of that base, A, times the height of the cylinder. And that's pretty straightforward and fairly simple math. That's kind of what we do with everything. The volume is the area of a base times the height. And we'll always sort of approximate that with here. Now, what if you have a shape that is not a right shape? In other words, it's not always this is a volume that is not a right. If the sides come in and they go out, what do you do here? Now, again, this is, okay, they changed their scale on it. This is a two-dimensional shape here that they don't give you what the other dimension is. But you split it you slice it into pieces. And if you slice the piece small enough, that this piece here, almost looks like a right cylinder. It isn't, but it's close. And if you just get your dy smaller and smaller and smaller, it gets closer and closer to being that right cylinder. Okay? And then the volume of that slice of this shape would be the area of that slice, approximately, at that point, yi minus 1 times your delta y. That would be the height of that slice, and then the area would be the approximate area of that. And they chose to use the bottom area to represent. You could have used the top one, it doesn't matter. It could have been a of y, delta y, just as easily. Okay? But we were usually using the base as the bottom. You think of base being on the bottom. So they use the area of this base times that height. As long as it's a narrow enough thing, that's going to be a decent approximation of that volume of that sliver. Okay. So divide the solid into thin horizontal slices. Each slice is nearly a right cylinder whose volume can be approximated as the area of the base times the height, which is your delta y in this case. So that's how we approximate volumes. Okay. Now, they go through a Riemann sum type. It's not exactly a Riemann sum, but that kind of analysis here. And your bottom line gets to be this. Goodness gracious. I think I can make it. I did not, I crammed down my salad, but I didn't drink very much, and I'm getting awfully dry, so if voice goes on me, I'll take a quick break and run down and get a swig of water, but I'll see if I can make it this way. So, volume is an integral of a cross-sectional area. Let A of y be the area of the horizontal cross-section at some height y of a solid body extending from y is equal to A up to y is equal to B. Okay? And you're going to let the A be the area of some horizontal cross-section of it somewhere along the way between A and B. And this can be changing as you go from A and B. But for one cross-section, it's constant. A as some function of y. Say at the base it may be quite big, then it may get small, then it may get big again. So as you go up, your A is a function of your height. Whatever that area function is, then multiply that by your thickness, your dy, integrate that from A to B, and that gives you volume of the solid. Yes. The tricky part here is getting that A as a function of y. If you get this, the rest of it is pretty much a piece of cake. So that's what most of your work will be, is coming up with what that area function is as a function of your height, your y. Okay. Does yours start with the volume of the pyramid? Okay. Like I said, all the work is going to be into getting the area as a function of your height. And here's how we're starting this. So, calculate the volume V of a pyramid of height 12 meters whose base is a square of side 4 meters. So, you know at the base, now what they didn't say here, it's a right pyramid. It's not a tilted pyramid of some nature. It's a right pyramid. Your base is 4 meters on the side, and your height is 12 meters. This is a big pyramid, by the way. 4 meters. I'm about 2 meters tall. The ceiling that put in about 3 meters tall. So the base would be twice. Okay. If I lay down on the floor, two of me are 2 6-foot people laying down this way and 2 6-foot people that way, that would be my base. And then we're going up, since this is 3 meters for 1 story, this would be 4 stories up. A 4-story building or a pyramid with a base of basically something greater than 12 feet by 12 feet.
So a meter is almost 3 feet.
It's more than 3 feet.
So it's pretty odd. I mean, it's just a tad over like a
Yeah.
yard, basically.
This is a yard, approximately, from your nose to the tip.
Huh.
This is about a meter. So
Oh, okay.
here to there. Yeah,
Oh.
just about a little over 3 inches difference.
Okay.
39 and
I
some
guess
fraction.
I've never made that association, but that's pretty
Yeah.
cool.
Yeah, it really is. Soccer fields are what, about 100 meters long? And a football field is 100 yards long, is that right? I don't play soccer, but
No football, you get the,
yeah, a football field is 100 yards long, and I think a soccer field is 100 meters long.
that sounds about right.
Yeah, so it's just a little bit larger. I remember when the Olympics were going to be in Atlanta, and we played some of the preliminary soccer fields games at Legion Field in Birmingham, that they had to redo the dimensions, and it wasn't much bigger. Okay, so this is a pretty big structure here. Okay, but whatever it is, horizontal cross section of pyramid is square all the way up. The base is 4 meters by 4 meters. Now, if you set this being the origin here, okay, then it's 2 meters this way, 2 meters that way, 2 meters this way, 2 meters that way. If you do that, you can do it that way. Okay. Now, what you need to do is to get the area of some cross section somewhere between, I don't know if they call it this, y is equal to 0 and y is equal to 12. Okay? You got to get somewhere up there. Okay? And the height above here is going to be your y. So y is going from 0 to 12. So there, somewhere up there at some height y, you have this slice. Okay? Now it's a pretty thin slice, we're going to call that dy. Right? That's the thickness here, dy. I'm surprised they didn't label that. I don't see it anywhere. But let me call this thickness here. Oh, I can't do it there. If I do this, it's going to shrink it. Let's leave it for a minute. Okay? That's going to be my dy here. Now, this is going to be, when you go y up here, all these are squares all the way up until you get to the point where it's just a point. Okay? 4 by 4 down here, something else up there. Okay? So go up y units, y something between 0 and 12. Minus 12, we don't do any y. So, you need to find the area. If your y units from the base, what's the area of that? Well, we know it's a square. Okay? And they say let each side of this be s. S here, S here, S here, and S there. Okay? Because it's a square going up. Okay? Now, the distance from the vertical axis here, and that would be S over 2, just like this is 4 over 2 here. So this would be S over 2. Now, here's where the magic comes into play, okay? This triangle right here is similar to this triangle down here. We know the dimensions of this triangle. It's 12 here, 2 there. Well, the ratio of this to that is also going to be 12 to 2. Okay? Well, this, if this is y units up, this length here that we need as our ratio is going to be 12 minus y. Okay, so now we've got 12 minus y is to 1/2 s, okay, as 12 is to 2. Well, that's our similar triangle. Okay. So, let's express that. Oh, now I think I've got to shrink. Okay, so, get my dark color back. So this is going to be my dy here, the thickness of that little plate. Yuck. There, okay. And then the ratio we just came up with is 2 is to 12 as 1/2 s is to 12 minus y. Okay. Where s is the length of that side. That's what we want to know, what the length of the side is. And that's why we can introduce that variable s, because once we know what it is in terms of numbers of y, which this is going to give it to us, we've got it done. So let's do a cross multiplication here. This is a proportion, two ratios equal to each other, and set that product equal to that product. So that will be 6s is equal to 24 minus 2y. Right?
Oh, that's right, yeah.
Okay? Now, next thing I'm going to do is divide out the 2 from both sides. That makes 3s is equal to 12 minus y. that makes S equal to 4 minus y thirds, wouldn't it? Dividing both sides by 3. There's what my length of a side is. The area then, that's what we're interested in. The area is equal to S squared. So this would be 4 minus y over 3 squared. Okay? Now, maybe I don't really like it in that form. I think that might actually be better. I regret I did it. Let's go back to this and just do it this way. S is equal to 12 minus y over 3. Just leave it in that form. That's actually better. So A is equal to 12 minus y over 3 squared, which you could write as 1/9, pull out the 1 over 3 squared, times 144, that's 12 squared, minus 24y, that's twice the product of the two, plus y squared. I don't know if that's any better or not. I sort of like it better. Check my math and make sure I did it right. I believe it's right. Okay. Okay. Now, actually, okay. I think oh, no, I'm all right. Okay. Yeah. Okay. So that's the area as a function of y. That's what we want. Now, the question was, what's the volume of that pyramid, wasn't it? Calculate the volume. V is equal to, what do we say the volume is equal to? The integral, bottom to top,
So what's that? A to C?
y equals 0 to y is equal to 12.
That's right.
Okay, times the area times the thickness, right? Here's the area.
12.
I'm going to do the 1/9 out front and do 144 minus 24y plus y squared times your dy. Right? I think it's raining. Okay. Goodness gracious. I'm not complaining, but we've had rain just about every day for the last awful long time, okay? Which is nice. I'm not going to gripe, but just fairly unusual. I did leave my windows up, of which I'm very glad. Okay, so this is equal to 1/9. Okay, what's the antiderivative of that integral? 144x, or y, yeah, minus,
24.
but half of that would be,
Negative 12y squared.
got it? And that is a 2 there. It's a pretty ugly 2. Y cubed over 3. Okay? Evaluated from 0 to 12. Afraid this one, the number is going to be pretty monstrous. But like I just described, this is a 4-story pyramid. Okay? So not trivial. 1/9 times 12 times 144. Anyone do that quickly on the calculator? Not so quickly. Second? 1,728. Okay, that sounds reasonable. Minus 12 times 144. That's 1,728, isn't it?
Which is 0.
That part 0 plus 12 cubed, which I think is 1,700. No. Yeah, it is. Okay. 1,728. You thought this was going to be hard, didn't you? Divided by 3. Okay. I'll do the 0 part. Okay, done. Okay, so this will be 1/9 of.
Oh, and it's 576.
Yeah, okay. You said it was what? 573? 6. 576. I don't hear well. Okay. And then 9 into that would be 64 cubic meters. They chose some nice number, didn't they? And that's exactly what they got, 64 cubic meters. See how that goes? The calculus part was easy. Figuring out what the cross-sectional area of that square was, that took most of the work. Okay? Make sense? All right. The next example, I think, is this one. Let's see if we can look at it closely first, and then we'll come back and do some calculations with it. All right. Sometimes drawing pictures are tougher than the other part. Compute the volume V of a solid in figure 4 whose base is the region between the inverted parabola y is equal to 4 minus x squared and the x-axis. Okay? And whose vertical cross-section perpendicular to the y-axis are semicircles. Okay. Whose base is the region between the inverted parabola y is equal to 4 minus x squared. Okay, I got it now. And the x-axis. Okay. All right. I wish they'd have put these in different order. If you drew the XY plane here, y being vertical and x being horizontal, and you do y is equal to 4 minus x squared. Okay? When x is 0, y is equal 4, right? When x equals plus or minus 2, then you're at 0. So this is minus 2, 0, there's plus 2, 0. Okay? And this is the parabola that would be formed by that. The sloping downward here because the coefficient is negative. You remember that from before. Okay. Now what we're going to do is their description, I think, was whose vertical cross-section, whose base is the region between the vertical pyramid, inverted pyramid, of y is equal to x minus 4, and the x-axis. And the vertical cross-section, and whose vertical cross-section is perpendicular to the x-axis are semicircles. Okay. So in other words, you take a semicircle and draw it here. We know that is radius 4, right? Because this is 2 here and 2 there. This is minus 2 plus 2. So that's going to be that first semicircle is a semicircle, semi meaning half of the circle, whose area is 4. Now, so what we do as you go up here, then the semicircles get shorter and shorter and shorter until you get there. It's kind of like, I could almost picture a tent being like this, a Quonset hut, kind of like an igloo, but an elongated igloo, you know, or something like that. You're getting less as you go back. So what we have to do is pick a slice somewhere here, and obviously the thickness is going to be dy again. Okay? Now, what we have to do is on this slice, we need to figure out what the radius is here. We know the radius here is 2. 2 here, 2 there. So the total is 4, but this is going to be a radius of 2 up here too. Okay? Back here, we're moving along here. Now, if y is equal to 4 minus x squared, okay, then here, when you're somewhere up here at y, your x value, okay, say you're somewhere up there, maybe from 0 to 4, so 1, 2, 3, 4, 1.5, anywhere there. The y value is this. We need to know what the x value is, because the x value is what that radius is. Okay? So what we need to do is solve this for x. Okay? How would you solve that for x? I'm going to have to reduce it. Solve that for x. Solve for x. Subtract 4 from both sides. That would work. Not quite, because that would be a minus x. Oh, okay. So why don't we add x squared to both sides and subtract y rather than 4? Okay. So that way this will go out and these will go out. Oh, I didn't put my plus x squared here. Okay. So that gives you x squared is equal to 4 minus y. So x is equal to the square root of 4 minus y. And that's how they got this. That's the length of any thing here, and that's also going to be the radius of that semicircle. Okay? So, to get the area of that semicircle, the area of a circle is what? No, pi r squared. Okay? And the area of a semicircle, 1/2 pi r squared. Where your r is this length here. Okay? So that would be, so that'd be 1/2 pi, and then it would be r squared would be 4 minus y. Okay. Works out sort of nicely that way. So that's the area of that little slice. Okay? We're looking for the volume, if I'm not mistaken. Compute the volume of that solid. The volume would be 1/3 AH. Okay. Okay. I'm afraid so. Okay. Okay. The volume would be the integral of that area. Now the area always has 1/2, so let's pull out the 1/2, or pi over 2. Let's pull out the pi over 2. Those are constants, right? And it would then be 4 minus y dy, because remember this is your dy here. The thick of that slice is your dy. The area of the slice is pi over 2 times 4 minus 1. So that's what we need to take the volume of. V is equal to pi halves. And this is going from 0 to 4, wasn't it? That's what the y's are going to. Okay? And this would be what? 4y minus y squared over 2, evaluated from 0 to 4.
That's 16.
Okay. 1, or pi over 2, okay, times 16 minus 8. Okay, I'll do the 0 part. It's done. Yeah, it's done. And that will be pi 8 pi. No, I'm sorry, 4 pi. 4 pi. 8 here, divided by 2, 4 pi. So that would be, did they give units? I don't recall. No, that says so it's 4 pi. So that is your area. Again, the crucial thing was getting the area of that slice. Okay, and in this case, we were given y as function of x, and because your x value here was your radius, you need the x as a function of y. So you have to flip those two over. So given this one, solve it the other way. And once you have that, you have the radius, and then the rest is pretty straightforward. Okay, sorry.
We're close.
Awfully close. Awfully dry. Okay. The next one's an even simpler one. I think this is one your eyes were going down to before.
Yeah.
Okay. Compute the volume of a sphere of radius capital R. Again, thank you very much for drawing the picture book, okay, and slideshow. Now, frankly, folks, we know the answer to this, whether you remember the answer or not. You should know it. So here is a sphere of radius R. Now, frankly, I wouldn't have drawn that to be my thing. I would have drawn it this way, but it doesn't matter. It works either way. So, a sphere of radius R, meaning everywhere from the center of that sphere to every point on that sphere, into the board, out of the board, and all, the sphere is always R units from the center. Okay? Now, what we need to do is cut this, and they decided to do vertical slices, which is fine. And they're cutting it in vertical slices, so since they're doing it in vertical slices, this is x, this is y, the thickness here is dx. Okay? Now, we need that area here, this random area here, to be in terms of x. Okay? I forgot your dx, because that can be your dx. Now, this is also a circle, but it's a smaller radius r. This one happens to be exactly r, the one on the axis here. This is something less than r. So how can we get what that is? Well, you've gone out x from the origin along the horizontal axis. You know this is always r to the tip here, so what you have to do is get this radius, which is the radius of that circle, in terms of x and r. How can you do that? Get this radius, that's what you need to do to get the area of that slice. You need this radius. You know you come this way x and that way r. How do you get this? If you know this is x, that's r, how do you get that? Pythagorean theorem. And what does that tell you? That this little r, they're calling it squared, plus x squared is equal to capital R squared. So therefore, the little r is squared, is capital R squared minus x squared is equal to little r squared. Take the square root, and you got the square root of capital R squared minus x squared. That's your radius. And what's the area of that slice then? Oh, I forgot to shrink it. The area of this slice would then be, that being the radius of that slice, pi little r squared. That's the area of a circle. Exactly. And that would be pi times, and the square of, a square root is just this, capital R squared minus x squared. Because you square a square root, you lose the square root. So that's the area of the circle that's x units out from the origin. Okay? What you reckon your integral is going to be then? Okay, 0 to r. Okay. You don't need to do minus r to r. You could, but same hemisphere there as you have here, so let's just double. So the total volume would be v is equal to twice the integral from 0 to capital R of, pull the pi out to, the r squared is r squared minus x squared dx. That's your thickness of that. Area times thickness will be the volume of that little slice. Add them all up from 0 to r and double. Okay, I think we got it done. Okay, now remember r is a constant, not a variable. Capital R is a constant. So this will be 2 pi, the antiderivative of capital R squared dx. Capital R squared x. You got it. Okay? Minus x cubed over 3. Okay. You evaluate that from 0 to r. Yeah. Okay. 2 pi r cubed minus r cubed over 3. Okay, I'll do the 0 done. Okay. Now, this will be 2 pi times r cubed minus r cubed over 3. That would be what? Be 1 r cubed minus 1/3 r cubed. 2/3 r cubed. Okay. And then multiply that. That would be 4/3 pi r cubed. If any of you have any doubts, front inside cover of the old book gave you the volume of a sphere is 4/3 pi r cubed. I don't know if the new books have that or not. And what I don't know, did some of you get the loose leaf books from the bookstore? Oh, you did. Oh, okay. If you did, I just wondered if they included the front inside cover. In my physics book, my physical science book, and the course I teach on Tuesday, Thursday, they left those off. They put this page, but they didn't put this page. This page is blank. I know.
Typically, those are the most.
Yeah, that's the stuff you turn to all the time, and they left those out, and it was not very pleased with it. But, I've requested specifically they remember to do that next time. Okay, so yeah, that's the area of a sphere of radius r, 4/3 pi r cubed. Now, we run into a guy named Cavalleria. I don't know how to pronounce it. I think it's an Italian name. It was back I don't know if this is absolutely true, but it seems like it was probably back about the time of Newton. It may have been before him. But we hadn't, well, couldn't be much before him because we're talking about integrals, but they may have been basically describing integrals but not really dealing with them. But a guy named, he was Italian, Cavalieris, I guess is how you say it, principle, is that solids with equal cross-sectional areas have equal volume, and if all those areas were the same, even though they're doing all sorts of weird things on the way up, if they're all the same, they're the same as that solid stack. Just think of a bunch of quarters, or these look like euros actually, I don't know what they are, stack of coins, and you mess with the stack. As long as they got the same number of coins in them, they're the same values, right? Haven't added anything, just looks a lot weirder, okay? So two stacks of coins have equal cross sections, hence the equal volumes by Cavalieris formula. I guess is how you say that. Principle. By the way, a couple of paper topics there. Who was Cavalieri? How did he come up with this principle? What are applications of this? Okay. All right. I think that's all we're going to say about that. Okay. Goodness gracious, my eyes are stinking. All lack of moisture. I'll just hang my head out the window and look up. Okay. Now here's a formula, and we're going to use it in gobs of different forms. Okay? But we're talking about density here. And you can talk about density in several ways. They're starting off with a rod or a pipe or something such as that. And that thing typically has some linear mass density. So much mass per unit length, assuming the cross sections are all fairly equal. Okay? So total mass would then be the linear mass density times its length. And they use for linear mass density the Greek letter rho, okay, times the length L. Okay? If you were dealing with area mass density, let's try to think of a decent example of this. And I'm guessing maybe that's as far as went. The area mass density, the total mass would then be the linear mass density times the okay. In other words, you have an equal area throughout, and its area mass density, I can't think what I think it's S is what they use for there, not S, sigma, the Greek symbol sigma for that. And then that would be times the length of that. And then other problems, you have solid mass density, and they go back to using rho for that one, I think. I'm trying to remember from the physics what they typically use. But we're just going to start with just linear mass density, where the total mass is the linear mass density times the length. Okay. And that's the formula for that. Here's an example of that. Let's say we have a length of 10 centimeters. I can't use this, but L is equal to 10 centimeters in length. And your linear mass density, rho, is equal to 9 grams, I think they say, yeah, 9 grams per centimeter. That's the mass density. Then your total mass, M, would be 9 times 10. It would be 90. The centimeters here, cancel the centimeters there, grams, okay? Which would be 9/100ths of a kilogram if you want to write it that way. Okay. Now, that's assuming that the linear mass density is uniform. In other words, it doesn't change. Trying to think of an example where you might have something that would change linear mass density. I can't think of anything right now, but supposedly people have done this before. Drilled out the center axis of a baseball bat and packed it with lead, and then put a plug back in the end, sanded it off so you can't tell it's there. They're called doctoring the bat. And then when they swing the bat, there's a lot more energy behind it, momentum behind it, so you typically hit further. And I've heard of that being done, not ever seen it done, but heard of it being done. So now consider a rod extending along the x-axis from x equal a to b, whose density up the rod, whose density rho is a continuous function of x, okay, as shown in this figure. Okay. Oh, here, got it. Goodness, I think we're about out of time, aren't we? Okay, I think I'm about out of dryness too. So what I'm going to do is let me give you just a few homework examples from this section. We'll start next time with this slide right here, and we'll go from there. Homework exercise, we didn't get very far in this section, but we did get started. I think you can do any of the odds 1 through 7. Those are all similar to what we did before. Then choose any of the odds 9 through 13. Those are similar to what we did before. Try to do 15 and or 17 and or 19 and or 21 and or 23. Okay, I think we're getting close to where, yeah, stop there. So the last part was any of the odds 15 to 23. Some of those get to be a bit complicated. but try to do some of those. And we'll pick up the rest of that next time. Good deal.